And welcome back. So, at long last, we are here at the Lorenz system, right? And we might be familiar with this. We might see all kinds of fun little graphics about this system. But allow me to start the video here by saying that this is a remarkably complex little system for having essentially minimal nonlinearity in it. There's a very complex set of dynamics that occur here. And what we're going to focus on in this video is going to be kind of a preliminary analysis. We're going to try to apply what we already know about dynamical systems and try to use our usual analysis to see what we can kind of parse out of this guy and see what kinds of dynamics we can expect. So a good portion of this is going to be a fixed point analysis, but at the same time, it's going to be a little bit different than what we're used to. We're going to analyze it in a little bit of a different fashion. So we have defined what we would like to find. We would like to be able to figure out what kinds of dynamical systems actually produce chaos. And what should we mean by that in this continuous setting? So we're going to focus on systems that have strange attractors in them. So I think between now and the end of the semester, we're really only going to have time to look at the Lorenz system and and either the Arnold cat map or just variations on Smale's horseshoe, the horseshoe map, and creating a strange attractor within the box, within a square. So at this point, let's just focus on what this system is. And the Lorenz system, named for meteorologist and mathematician Ed Lorenz. This is not the same as the physics Lorenz, like Lorentz transformations. No, that Lorenz has a T in his name, Lorenz. This is Ed Lorenz. So he studied, Ed Lorenz studied this back in 1963, and he was effectively just trimming down an atmospheric model that he was studying for a model of convection rolls. So this is a mixing of when warm air from the surface mixes with colder air in high altitudes. So what we wind up with in this dramatic oversimplification of that nonlinear model, that extraordinarily sophisticated model, is actually just the set of three different equations here. And it is essentially already non-dimensionalized. So we don't have to do that analysis, thankfully. But we do wind up with a system that has three parameters in it. It's got sigma, it's got r, and it has b for the state variable and state variables x, y, and z. And those are literal coordinates, right? So a solution to this system tracks a particle, right? So an air molecule. It doesn't quite make sense. Air is composed of a lot of different things. But let's say we were tracking a small volume of air, a very, very small volume of air, as it flows through this system. And what a solution x is going to do here, x vector of t, is going to track the motion of that particle, or at least that little collection of particles, as it's heated and cooled and rolled around in this system. Specifically, for some context here, sigma is what we call the Prandtl number, and it measures so when we're talking about gases or just ensembles of particles, we have to talk about like group momentum and group diffusivity or group temperature, group kinetic energy. And these are what we have for the following ratios here. We're talking about a ratio of the group momentum's diffusivity, so how much momentum wants to dissipate, against the thermal diffusivity, saying how much heat wants to diffuse through that little ensemble of particles. Similarly, the parameter r we call the Reynolds number, and it's effectively telling us the ratio of inertial forces to viscous forces. So how much this guy resists motion because of its group mass versus how sticky this substance is, how resistant to flow this fluid is. But apparently there's no well-established name for this parameter b that shows up. However, it does control effectively the aspect ratio of the elliptical shapes that we see in the roll currents when we actually carry out this, when we simulate what happens in this model. So we'll go ahead and study this system in a moment, but it's really fun to see what happens if we just go ahead and start plotting this thing. And I have a little routine here called the Lorenz system, or Lorenz system, and this is a little MATLAB script I made for myself. And what I'm going to do here is see exactly what happens in the system when I give it, I don't know, 5, 10, and 15, say. Right, so what I have here in the first parameter is the total time, little t, for which I would like to run this simulation, and I'm giving it the initial condition x, y, z, or x naught, y naught, z naught, and that's 5 by 10 by 15. And that's it. That's all I have to do here. If I don't suppress the output, it is going to give me a gigantic list here. It's going to be, what, a 10,000 by 3 dimension, or sorry, 100,000? Yeah, 100,000 by 3 dimensional matrix. So let's go ahead and suppress that output. However, when I do run this guy, I am going to get a couple of plots. And the first, well, wait, I'm supposed to see something really, really awesome and complicated in here. Come back to that. But look what happens if I zoom in here. Oh, shoot, I should pan first and then zoom. Bring that over this way. See what we find. Yep, move way over. Yep. Ah, here we go. So notice let's see. I believe it's going to be the blue curve that corresponds to the initial condition 5. The red curve corresponds to initial condition 10. Yep, and then the yellow curve or orange curve, depending on what you see, is going to be the 15. So blue is x, red is y, yellow is z. Okay, and that's what I want you to keep in mind moving forward. It goes blue, red, yellow, x, y, z. But more to the point, look at what happens to these guys. They die off really quickly here. They go to zero. They go to the origin very, very quickly, and we see that in a three-dimensional plot of this system. But again, we're supposed to see something dramatic, something new, something really chaotic looking and just kind of beautiful in its own right. But what happened? If I come over here and highlight this line, that Reynolds number actually plays a significant role in this system. And we're going to see that in part of our analysis. It turns out sigma is also going to have a significant role, and so will b. So all of these parameters actually do govern a certain amount of complexity in the system. But notice where I started. Reynolds number of 1/2. So just to put it in perspective, the default for the system is 28, and that's a number that Ed Lorenz used himself. And in particular, let's see, if I remember, let me actually look this up on Wikipedia, but air has a Reynolds number roughly, if I remember correctly, on the order of tens, so either somewhere between 10 and 20. So we are cutting down that Reynolds number very, very dramatically by 2 orders of magnitude. But look what happens here when I change that. So I'm just going to go ahead and save the file real quick. It's going to tell me bad doc sheet, bad. But then I'm going to use the same initial conditions, but for a different R value. I'm going to increase the Reynolds number. And it'll take a second to compute this, right? I'm doing this for 100,000 computations here, 100,000 points. So I do see that asymptotic behavior again. However, it doesn't go to 0 anymore. In fact, I start to see the notorious spiral start to show up. That's going to be very important for us in a little bit here. But let's bump up the analysis here. Let's go to, say, 20. We'll go a little bit further here, get in the range of what normal air, the Reynolds number for air looks like. And, come on, you can do it. It helps to encourage the computer, but look at the oscillations now. These guys are still trying to home in on something asymptotically, but now notice that these guys are actually oscillating. Right? Very, very, very small oscillations, but they're starting to oscillate. Right? And be sure you note the scale on these axes. But look what happened. This guy came in and started to think about going to this what would appear to be a fixed point, but it's just oscillating around it. It's trying to home in on that, but somehow it can't. And now the fun part. Let's see what happens. Let's see what Ed Lorenz saw. Same initial conditions, same time. What do we see now? Sheer and utter chaos. There's no periodicity in here. However, there is beauty. We do see this crazy surface-looking thing that showed up out of nowhere. And this is what's known as the Lorenz butterfly, or the Lorenz attractor, right? Where we're seeing the shadow or like a hint of it with this solution. So I can't rotate this in MATLAB Mobile, but you can in just about any other MATLAB IDE. But the point is that this guy is very symmetric, and there's something here that we're not seeing or that we need to find in our analysis. So let's see what we can actually scrub out here from the beginning, just from an initial look, a cursory glance through what the system behaves, or how the system behaves. So let's look for fixed points, and you can do this pretty quickly. If I label equations here from top to bottom as A, B, C, equation A tells me that fixed points have to occur on the plane x equals y. Sure, I'll buy that. That's exactly what we see in our numerical simulation. Equation A and C, however, means that x and y have to be the same, so I get an x squared equals bz, so z is equal to x squared over b. That's going to be one that we need to take with us moving forward. But equations A and B together, if I let x equal y, then I'll wind up with r minus 1x minus xz is 0. So either x is 0 itself, and that would mean y would have to be 0, so I'm sitting somewhere on the z-axis, or that the z component is just r minus 1. And we'll see, for interesting solutions, we want to look at r minus 1. But we'll take care of both cases because we are nice and thorough. So if x is equal to 0, that means that y would have to be 0. But notice that this star equation up here says that if x is equal to 0, then z must also be 0. So that means that the origin is a fixed point. And you look at this system and you say, well, you look at this system and you say, well, duh, yeah, I can plug in x equals y equals z equals 0, and sure, this satisfies the equation trivially. But the interesting thing to note here is what happens. You can actually verify that this origin is always, right? The origin is always a fixed point, regardless of which parameters you use for the system, so long as they're positive. All right. Now for the case where z is equal to r minus 1. Right, we go back to the star equation up here. If z is equal to r minus 1, then I multiply the b back over, and I take the square root, plus and minus, on both sides, so that x and y both have to equal plus or minus square root of b times r minus 1. Hence, we actually get a pair of fixed points. And this is plus or minus square root of b times r minus 1 for both x and y, and r minus 1 for z. And we notice that these fixed points can only exist when r is greater than 1. Right? If it's equal to 1, then we're sitting on the origin, and we already know that exists. But these particular fixed points only exist for r greater than 1. That seems to indicate there is a bifurcation in the r value, in the system, for r values. And specifically, it looks like it's happening at the origin. Let's see if our linearization can detect this. So you can go ahead and compute the Jacobian of this system. And for the most part, it's actually not terrible. There's a good portion of do-nothing computations. But we evaluate this... oh, shoot, there's the eraser again. We evaluate this Jacobian matrix at the origin and at the plus or minus, or the c plus and minus fixed points that we just computed. So C plus will correspond to the plus square root. C minus will correspond to the minus square root. But it turns out that these guys have very similar Jacobians. And notice that the plus minus down here is very much sensitive to which sign is above the other. So for C plus, we're going to go ahead and use the minus square root for this term, but the positive square root for this term, and similarly for this guy. But if we're using C minus, then we're going to go ahead and use the plus term, the plus square root for this guy, and then the minus square root for this guy. Okay, so that's all that that notation means. I'm just trying to compactify my analysis here a little bit. So now we're going to go and, so at the origin, actually, we also get a Jacobian that's very nice, very, very pretty for us. And it will, we'll analyze that in a moment. So from our usual trace and determinant characterization of eigenvalues and fixed points, well, no, we can't actually use that because that was only for two-dimensional systems. Specifically, it was for characterizations in the plane. So our eigenvalue dichotomy here, or that characterization of eigenvalues and fixed points, no longer applies. We can't use it. However, we still can compute the eigenvalues directly. It's a little bit more painful, but we can still do it. At 0, the eigenvalues of J0 can be found thusly, and you will see that there's this nice factorization where I can pick up a lambda equals minus b, and lambda equals this mess from the quadratic formula. But the thing to notice here is what happens if my r value is in a certain parameter range. So we'll talk about that in a moment. Right? So specifically, the thing that we're going to look at is what's happening in this term. And notice that that r equals 1 shows up again in that term. So we might actually be able to see the bifurcation that we expect in the Jacobian, or in analyzing the Jacobian. And if we want to go ahead and compute the characteristic polynomial for this guy, yeah, go ahead, have fun. I actually did try to do that by hand. It was not fun. Don't do it. Use a symbolic algebra machine. So please, computer algebra, just get it over with. Show that the characteristic polynomial is the following cubic. Have fun doing it by hand, really. I don't know if it's really worth doing this by hand unless you want the actual practice. You want to be able to verify that I'm not blowing smoke up your butt. Sure, go for it. But the eigenvalues are a little bit trickier to come up with. 3 numbers. But there are 2 observations here. The first is that if I use r equals 1 in either of these, then there is a 0 eigenvalue. And that should make sense because at r equals 1, the origin and c plus or minus are all the same location. So something is happening here where I go from 1 fixed point to 3 fixed points, and that should scream at you, pitchfork. All right. The second is that j of c plus or minus of either of these, right? The Jacobian of either one of those non-origin or non-trivial fixed points. It turns out these guys have exactly the same eigenvalues. And we'll see why that's not so strange in a moment, but those guys behave nearly identically. No, they behave identically, just as rotational symmetries of one another. So let's actually see what happens at the origin. So geometrically speaking, if I'm at the origin, then what I'm looking at here is for r less than 1, then this term, this sigma plus 1 squared minus 4 sigma times 1 minus r, if r is less than 1, but still positive, then the thing inside the square root is going to be less than sigma plus 1 squared, which means that the actual square root here is going to be less than sigma plus 1. So that means that I'm taking a negative, when will I learn? I'm going to take this negative sigma plus 1 and either subtract more off of it or add less than sigma plus 1 to it, which means that both of these eigenvalues that I get on this end are negative. So that means that I have 3 negative eigenvalues and I have a stable fixed point at the origin, and that's this picture here. The origin locally is drawing solutions in from all directions. However, the minute that I cross r equals 1, again, I'm still taking off some non-trivial amount from negative sigma plus 1. But if I add that square root instead, and I wind up with something where 1 minus r is actually a positive number or a negative number, then the thing that I'm adding to the negative sigma plus 1 is actually bigger than sigma plus 1, and this eigenvalue flips. So that means that I change stability in one of my eigendirections, and you can see that this actually occurs in the z direction. So there is a pitchfork type bifurcation here where I have sacrificed stability in some direction to spawn off 2 more fixed points. Now, if we are in the range where r is less than 1, we can actually do better than say there's local stability here. We can actually show that this fixed point is globally attracting, so it is a global stable fixed point. And much to my surprise, at least, there's actually a Lyapunov function for this system in this parameter regime when r is between 0 and 1. And you can go ahead and compute this. You can double check my algebra here. What we're trying to do is figure out if this L function, this L of x, y, z, is decreasing along trajectories. So I'm taking d dt, remember, of L of x of t. And that's what this term is here, this L dot. And what I wind up with here is through the chain rule, I get a gradient dot of velocity, and I can follow the computation through to the bottom of the set of equations here and show that this L dot is decreasing only if I can guarantee that this guy is negative, which if I flip directions and divide out the 2 sigma, I need to make sure, so L will be decreasing if and only if I can show that this quantity, and I'll make sure I point it out, this guy, make sure that this guy holds. So that z squared is no problem. That guy is always going to be at least non-negative, and if I'm not on the xy plane, it will be strictly positive. Great, no problem. So let's ignore that term for right now and focus on the fact that I have this mixed term of an xy floating around. Now, you can go ahead and figure out lots of different ways to show that this guy is positive, but the way that I'm going to do it is just by simply completing the square on this total term, x squared minus r plus 1 times xy plus y squared. We can complete the square and get down to this term here. And sure enough, if r is less than 1, then r plus 1 is less than 2, which means 1 minus, well, effectively 4 over 4, something less than 4 over 4. Right? That means that this coefficient that's attached to the y squared is going to be positive. Right? And then, of course, a square term. I completed the square. The squares are non-negative. So, provided the parameter is less than 1, I can go ahead and guarantee that this function, L, is a Lyapunov function centered at the origin, so the origin is actually globally attracting. Which, again, is kind of surprising to me, at least. Like that's kind of a big deal that you can do that. Right? Now, let's turn our attention to the C plus or minus points. So, R needs to be greater than the bifurcation parameter. Right? It needs to be bigger than the critical point that we passed. So, R has to be bigger than 1 in order for these guys to even exist as fixed points. And when we take a look at the characteristic equation, not just the polynomial for the Jacobian, we actually wind up with exactly the same characteristic polynomial. And this characteristic polynomial I will go ahead and name f, just for the heck of it. But the claim here is that the points c plus and minus are locally stable if we are within a particular parameter range. All right, and for the traditional, the default Lorenz system, this is approximately 24.7. Right. So let's go about showing this. So notice, when we are at the bifurcation parameter, when we are at r equals 1, then I can go ahead and factor this system. We already noted that the constant term goes away so that I have a 0 eigenvalue. That's what causes the bifurcation. But notice also that I have 2 other eigenvalues here, and I'd like to say that they are distinct in general because I'm not just dealing with Lorenz's default parameters. So I need to make sure that I'm using arbitrary parameters here. So if we are making the assumption that we are greater than, that our parameter r is bigger than 1, then notice that I've also put out that parameter there. I'm dividing by a sigma minus b minus 1, so it's a bit ad hoc here. But in order for this total algebraic expression to be greater than 1, it at least has to be positive. And the only way that this guy is going to be positive is if I can make that denominator positive. So that's the condition that I'm throwing here to say that sigma minus b minus 1 has to be greater than 0. And when I do that, I get the relationship between minus b and minus sigma minus 1, which is exactly this guy up here for my eigenvalues. So I can show you that these roots, right, the eigenvalues associated with c plus and minus are actually all distinct. So that means that I have a characteristic polynomial that looks like this. All right, I have a characteristic polynomial. So this is the graph of f. As we increase r, I mean, you can actually play with this numerically and see what's going on. What's really happening here is a combination of things. One, we are lifting this polynomial, we're lifting the cubic. We're also moving this little trough here. That trough is going to lift up and cross the lambda axis and then move to the right half plane. Right, so it's going to do that in a very specific order, and we want to keep that in mind. So it's going to move up and then over, right? So that's what I'm trying to show in the sequence of pictures here. As we increase, starting at 1, the cubic wants to lift in a very particular way, where we are going to keep, not necessarily exactly at lambda equals negative sigma minus 1, but we are going to keep the far left negative eigenvalue, but we are going to lose the two roots here on the right. And we would like to ask for the smallest value of the parameter r, and we're going to call that r sub h, where f of sigma actually has a root with real part equal to 0. Right? And because of the way that we're increasing the parameter, we're fixing sigma and b, but we are moving r. The way this is going to happen, remember that this trough lifts up first so that we lose those roots, and then we move over from the negative real side, or from the negative side to the positive side in lambda. And that's exactly what we want here, because that tells us that our roots take a very particular form. That means that we go complex first, and then we cross the real axis, or the imaginary axis. So that means that our eigenvalues, as we find the location where our eigenvalues have a real part equal to 0, it means that they have to take this form. They have to be pure imaginary numbers with a non-zero frequency, or non-zero multiple omega. So if I substitute that into this characteristic polynomial f, I will wind up with the following expression, which I then need to set to 0. I need to figure out where the roots are. I need to figure out when this occurs, or I got to figure out what my eigenvalues are, and those are going to occur for a very specific value of omega. And that omega I actually really don't care about. It's the r, the sigma, and the b that I care about. So if I set my evaluation to 0, I get my eigenvalues, and I see that as a complex number. I get real part plus imaginary part, and it has to be 0, so that means that both the real and imaginary parts need to 0 out. And what I wind up with is this curious string of equations where I can totally omit what omega is. I really don't care what omega is. However, I do care about the relationship between r, sigma, and b. And following a little bit of algebra here, we wind up with this for our value of r sub h. And this is exactly what the... Did I do that? Did I do that right? Uh-oh. Might have to double check my algebra here. But I digress. We do wind up with... Yeah, I may have written it down incorrectly. We'll see. Let me get back to you. So notice that we do wind up with a minimum value where this occurs, and that's the point. I believe... let me check my code, because I actually put it in the code for the Lorenz plot. Yeah, okay, so the statement of the theorem is correct, but my algebra might be a little off. So I will go back and fix that in the notes very, very shortly. But the point is that this guy occurs, like there is some bifurcation in here that changes the stability of a cycle, of a spiral specifically, where we go from a locally stable node that turns into a spiral, right? Yeah, so let me just walk through it. This guy is stable because the real parts are all negative over here. Even when we switch into an imaginary number, the trough here is going to occur to the left, right? It's going to be to the left of the f-axis, which means that it will have a negative real part, so that this node turns into a spiral, but they are still stable. And the interesting thing that happens here is that I keep my fixed point, but then I switch off the stability. So I go from a stable spiral to a stable node to I go from having stability to having instability at the fixed point and an unstable limit cycle, as it turns out. So in particular, what the remark here says at the bottom is that a Hopf bifurcation, in fact a subcritical Hopf bifurcation, occurs at this parameter at r, h, and at the points c plus or minus with bifurcation parameter r sub h. The analysis to show this is a little bit trickier, and there are references in your textbook that can point you in the right direction if you're curious about it. But the points c plus and minus both change stability at this location and in fact become unstable. And this is about as far as we can go with our preliminary analysis with techniques that we know from the plane, right, from the phase plane, from Lyapunov functions, from limit cycles. Just about anything that we have, we're throwing the entire kitchen sink at this thing. And we're only getting so far. Next video, we're going to see what other techniques we can use, what other properties we can kind of scratch out of this system. So